Yeah. So the another important feature that was there, that was feature engineering. That is why we prefer deep learning. So for normal or classical machine learning algorithms, what is the workflow is we have got an input, consider it as an image of a cat, and we do feature engineering. So we'll have to manually define some features for those machine learning algorithms. For example, detecting edges, detecting eyes, you can say, detecting ears. So something like that, you will have to manually do feature engineering before passing it to the machine learning or classification algorithm. And once you do this feature engineering and you have passed to a classification algorithm, you get an output that, yeah, it is a cat or a dog. So if it is not a cat and you have wrongly predicted it, then you will have to manually work on this feature extraction, or you can say add some more features that will be correctly classify this image as a cat. While if you go to a deep learning workflow, there would be an input and we don't have to do feature engineering, and we'll pass it to a multi-layer neural networks, and that will help us to extract features on its own. So behind this, what features are extracted, you can visualize it, but that is done all by itself and without, or you can say with minimum user intervention, and that features are again used for classification, and you get the output as cat or a dog. So the entire feature extraction or feature engineering can be accumulated in the entire deep learning network that we have. So we don't have to manually invest time in that thing. But yes, some feature engineering is obviously required, and it's not like fully automatic that you just provide a cat image and that's done. So you have to do some pre-processing, but that is comparatively less compared to machine learning. And this is the two major advantage that we have talked about why deep learning is important rather than machine learning. So we can easily generate complex decision boundary, and feature engineering is again simple compared to machine learning. So now we'll go to artificial neural network, or you can say single layer neural network, or MLP. So as I already mentioned, these are also known as function approximators, universal function approximators. So it can approximate any function that you want to uh, predict basically. But yes, so if the function is more complex, then more number of neurons are required in this hidden layer, and that will increase the number of parameters that algorithm needs to train on. So it has got capacity to learn weight. So that is what we call it as the parameters. Those are weights of the system that are learned by the algorithm by just providing the data and the prediction level. So that how it is done, I'll just show the GIF image after this. So as in the neuron example, I have shown that we have got these three values that are coming in. We sum that up, and then we pass it to a non-linear activation function. For example, in that we had sigmoid was there. You can use any 10H or ReLU. ReLU is more popular nowadays. So when we pass these signals to that nonlinear activation function, we can add some amount of non-linearity to the input data. And due to that, we are able to work on more complex decision boundary rather than a simple linear one. But as already mentioned, this has limitation that it loses spatial features. For example, in the image where the eye is located, and all that spatial features are missing in the pixel because we have to convert it to a 1D feature before passing it to MLP. And another is it loses the sequential information that is required in natural language processing. So how does it work? So for example, these are the feature vectors. or you can say features that are input to the hidden layers. And this hidden layers then calculate the non-linearity passed to another layer. And finally, we get as something what is predicted. For example, in the case of a cat and a dog, if we have input as cat and for the first time it is predicted as dog. So when you calculate the error, means the actual label is cat, but we are predicting as dog. So we calculate the error by what amount it is getting wrong result, and that error is being propagated backwards. So this is the feed forward, you can say, cycle where we input the image and we get the prediction. Now, once we get the prediction, we calculate the loss and that we basically propagate it backwards. That is called as back propagation. And using this back propagation, we can just update the weights of these individual hidden layers. And this is then been stabilized after a few iterations of forward and backward propagation. So there is a lot more mathematics behind it, but we'll not go into detail of that. And most of you must already know how the stochastic gradient descent works behind this algorithm and all these things. We'll not go into detail about this. So this is how a neural network works. This feed forward, calculate the loss, and propagate the loss to the backward and update the weights. So you will be able to see the derive and update state. Yeah, derive and update the weights here. Now, to, to overcome the limitation of this MLP, we go to the convolution layer neural networks. So in convolution is basically we work upon some kernels, or you can say filters, where we pass it on the input image and we extract features based on that kernels. And convolution is just a multiplication operation between two matrices in simple sense if you consider it. We'll go in the next image what actually multiplication takes place on. And it, because of this, we are able to capture the spatial features like the pixels surrounding the interested pixels, how it is structured. So the structure information in the image has been captured using this kernels, or you can say filters. And this is the advantage of convolution neural network. So with this, we can the same kernel is basically passed on entire image. So you can find the same feature on the entire image multiple times as well if it is available in the same image. So it helps us to identify the object accurately, where it is located, and the relation between the object and the image. So it takes a surrounding pixels as the uh, so it takes care of the surrounding pixels, and we can get the understanding about the relation between that object and this particular image. So this follows the concept of parameter sharing. That is the thing that I mentioned, that the same filter is applied on the entire image. And even if the feature is present in different location of the image, we will able to identify that in that particular location as well. And this produces a feature map. So what is feature map will come at out. So now when we go to how this convolution neural network works, so there is an image, and instead of 1D input, we are having a two-dimensional directly input. So the entire image, these are the pixels that are there. Now it might be color or grayscale. So depending upon that, the number of channels would increase, but we'll simplify it for now. And these neurons are then passed through a hidden layers where nonlinear activation take place. There is some pooling involved. What is pooling will go in the next slides. And finally, we get the prediction that it is a cat or a dog. Now, same thing as the MLP, this is the feed forward side, you can say. Uh, this is the feed forward side of the algorithm. Now, once this is classified, we compared it with the truth value, means if we have classified it correctly or not, and based on that, we calculate the loss. This loss is then propagated backwards to these neurons, and these neurons are then activated correctly based on that particular loss. And we try to reduce that particular thing so that we get the correct results for, or you can say generalize this for multiple input values. And that this step is called back propagation, as we have already discussed. Now we'll move on to convolution. What is convolution? So in convolution, we mentioned something about filters. So consider this yellow 3 by 3 matrix, which is 1 0 1 0 1 0. So this is the filter, and that filter is been slided on to the image to get the output convolved feature. So what we do is we multiply the filter values pixel by pixel, sum it on, and update the center pixel value. So for example, this is 5 by 5 image, and we run a 3 by 3 kernel. So we are getting 3 by 3 output here. And this particular cell will be updated. The center cell is updated for the convolution, and we update this filter. So after passing this filter, what features we are getting is this, the pink color one. As we are passing this filter or same filter in the entire image, we are able to detect that feature anywhere in the image. And this is where the translation invariance, the main property of convolution neural network, comes into picture. So that feature, it is anywhere in the image, we'll able to identify it. It is not just that if it is at this particular location, then only we will get that feature as an output. Anywhere in the image. And this is the main property, translation invariance. So even if the image is slightly rotated, or it is slightly cropped, or it is, you can say, squeezed off, but based on the filter, we will be able to get that location of that particular feature anywhere, right? So this is convolution. What's the size of feature matter in selecting feature? So the filter size is, you can say, hyperparameter, or you can say, uh, so the size is not actually dependent, because we will go into the next layer, that is called pooling layer, where we aggregate the, or you can say, scale the image slightly. And due to that, even in that case, we are able to get the feature that is there. And the kernel size that is there, that is hyperparameter that you can set while deciding the hidden layer. And yeah, so depending upon that, you will be able to slightly get different outputs compared to 3 by 3 kernel. If you use 2 by 2 kernel, then it will slide two slides at a time, you can say 4 by 4 pixels at a time. So based on that, the features would be slightly different compared to what we are getting in 3 by 3. Okay, so we'll come out to feature map. What is feature map? So consider this is an image, and the small thing is the filter. So the size of filter is usually less compared to the input size of image. And due to that, we are able to move that filter at multiple location in the same image, right? If it is of the same size, then you will be able to just detect one single feature in the image. So that is why we are using a filter size that is less compared to the input size of the image. So when you convolve this filter to this particular, consider it 3 by 3 block, you will get a single value as output. This single value as output. And this single value would be a single pixel value of the feature map. Consider like that. So if you go into this image, so when you convolve this 3 by 3 pixels, you will get a single value here. So this is a single value of a feature map, you can consider it, as shown in this image, right? And when you slide the filter again for the next particular set of input, you will get another single value, and that would be the feature map second value, right? So this is called a feature map, the individual you can say intermediate images that you get when you apply a convolution layer. Now the pooling layer. So the pooling layer is just basically, you can say, aggregating the information between some sets of pixel. So for example, for this particular image, if this is the pooling kernel, it will average out and just give one value for that particular block. And you will scale down the feature to just 2 by 2, right? So why this is required? So in feature map, so in this feature map, when you find the feature here and add it to the pixel value, so this is not translation invariant now. So if you slightly change the image, or you can say if you slightly crop the image or rotate the image, then this feature vector, feature map that is there, that is slightly different compared to what it was there. And this loses the translation invariance that was the main advantage of convolution. So to bring that back into picture, we basically average out, or you can say there are multiple pooling layers type. Uh, Consider it averaging out the values of that particular location. Then we will get back those translation invariant back. So if you see small movements in the position of features in the input image will result in different feature map, as I just mentioned that. And due to that, we'll get the different result in the next layer. But we don't want that. We want that to be translation invariant. If the same image is rotated slightly, but the feature is that, so if a ear is rotated, or you can say if eye of a cat is rotated somewhat, but it is still an eye. It is not like a rotated eye is something altogether a different feature. So we want to detect that rotated feature again as an eye itself, and that is why we apply pooling layer. And this is in general, whenever you use convolution neural network, after one convolution or two convolution layer, we generally apply a pooling layer to aggregate that individual features that we have detected. And this can be done again by downsampling of image, but the better approach is to use the pooling layer. So as you can see, this big image is now convolved to only just 2 by 2 image and with this particular feature values. So this is more robust pooling layer. Now I will just explain the three types of pooling layer: max, average, and sum. So it's nothing. So in this uh, 2 by 2 neighborhood, whichever is the max value would be considered for max pooling value. For example, in this 4 block, 6 is the max value. So we'll get 6 here. In this also 6 is the max value. So we'll get 6 here. Here 4 is the max value. So we'll get 4 here. Same thing for minimum and averaging and summing. So for summing, all these values would be summed. Average, all these four values will be average. And this is the values that we get after applying the max pooling, average pooling, or sum pooling layer on this particular feature map. And these are just the majorly, or you can say most commonly used pooling layers. There are more advanced type also available, but majorly this max pooling or average pooling is used. Now, global pooling is one thing where the entire feature map would be squeezed into just one value. And this type of pooling layer would be required in the output of the convolution neural network. So generally we use softmax, that is another thing, but this global pooling is also one thing that can be used. So entire feature means entire this 4 by 4 matrix would be generating just one value, and that can be maximum, average, or sum. That depends upon what type of operation you define. So yes, so because of this pooling, we get translation invariance on the feature map also. So still convolution neural network has that property restored because of this particular layer. Now, if you consider this convolution neural network, this is the input image that is there. So this is 32 by 32 pixel image. So consider there are 32 row columns and 32 rows here, right? And we apply 5 by 5 convolution here. So consider this currently 5 by 5 image, and we are applying a 3 cross 3 kernel, or you can say instead of this 5 cross 5, we will apply 3 cross 3. So what happens is we'll apply this here. and the size of the image would be reduced. This layer would be gone and this would be gone, and we'll get this. So now the size would be reduced by one row and one column if you use 3 by 3. But for 32 by 32, and if you are using 5 cross 5, then there would be two rows reduced, or you can say if you consider 5 cross 5, then this will be gone, this would be again gone, and that is why the feature map size is reduced, right? And then once we get feature convolution feature, we then basically apply subsampling, means you can consider it as a pooling layer, and that pooling layer again reduces the 28 cross 28 to 14 cross 14 metric size, or you can say the feature map size is now 14 cross 14. So once again we apply a convolution 5 cross 5, we reduce the feature map size to 10 cross 10, and that again we subsample, or you can say pool it. So you can see the basically what sequence we follow. We do a convolution, we do a pooling. So this goes hand in hand. Now again we do convolution here, and we again do pooling here. So now this 10 cross 10 feature map, when we pooled it, we get this basically 5 cross 5, or you can say 25 nodes basically. And this is then passed through the MLP, or you can say fully connected neural networks, where these individual nodes are input to the neurons, and then we basically get the output that here we get some probabilities here, or you can say some activation function values, and we pass it to a softmax generally, which basically turns that value into probabilities, and that probability is based on that, whichever is maximum probable value, we output that. For example, in this case, there would be the probability of 3 number would be highest because the input is 3, and we then predict the label of this image as 3. So this is in general, you can say, architecture of convolution neural network, and you will follow this same for most of the cases. It is just that the number of layers or number of this filter size that you use, uh, that would be different, and based on the problem, the output layer would be different, and that is the main reason now we have got transfer learning topic that is there. We'll not cover that here, but we'll use the same architecture, just change the output layer, and we are still able to get very good classification results for the pre-trained models that are there, like ResNets and ImageNet and etc. So that is transfer learning. We'll not go into detail about that. Mm, okay. So now we'll go for the main thing that we are here for, introduction to graph neural networks or graph nets. So for introducing that, we'll have to first understand what is graph. So graph is nothing but it's just a simple function with vertices and edges. So V here is vertex and E is the edges. So the nodes and edges can have features. So that is additional thing that they can have. For example, if you can see here, this A is the node, and the connecting between A and B, the link between them is the edge. So this is a simple graph that is there, and you can see there are no arrows here. So this is not a directed graph, it is undirected graph. You can see edges do not have direction. So it is just mentioning that it is a link there. But in the same case, if there is a direction involved here, that in which direction the link is attached for this example, then the graph turns into a directed graph. So for example, from D you can go to A, but from A you cannot go to D. So this type of graphs are generally used for shortest path algorithm and etc. There is another type, weighted graph. So for example, the edges have some weight. For example, if you have this 4 and 2, the weight for this A to B is 4, or you can say the length between A to B is 4 and A to C is 2. So there is more probability that we might go A to C, something like that. So this is called a weighted graph where weights are also attached to the edges. So in general, graphs are just this thing, function of vertices and edges, you can say. So graph representation. So consider this graph. So I just want to know, graphs cannot be understood by computer directly, right? So if we want to use in some machine learning or neural network algorithm, how you will represent graph? I want an answer. So how this graph can be represented in a computer? Anyone? Correct, Akshay. This can be presented as a matrix. Do you know what type of matrix, Akshay? Okay, no issue. So Akshay is correct. So the graph can be represented as a matrix. It can be n cross m, where n is the number of nodes and m is the number of edges, right? So computer doesn't understand graphs, so we provide it in the form that it understands, and that is a matrix form of this same particular graph. So consider this number of nodes here, A, B, C, D, E, and F. We have this nodes and the edges between them. So A, B, B, C, A, C, A, E, A, F. So all these edges are mentioned in the columns. And wherever there is an edge between those two, we'll have a particular value there. Or if edge is present, we'll have 1. If edge is not present, we'll have 0. So this graph can be represented as this particular matrix in the uh, computer, basically. So there is another, or you can say, adjacency matrix form, where this graph can be efficiently described in that matrix form. So it's a square matrix. So as you have seen in this thing, this is not a square matrix, and generally square matrices are better. So for this adjacency matrix, it's a square matrix. So what will be there? There would be uh, nodes listed on the rows and columns. And wherever, for example, okay. So consider currently there is no self loop. So I will just show this. Yeah. So this is A node, B node, same thing, A node, B node. So currently there is no self connection. Self connection means A is not connected to itself. So between A, there is no edge there. So we have a 0 here. But between A and B, there is an edge present. So if you see A and B, there is 1 here. And again, with B and A, there is a 1 here. So it's a square matrix. So you can say symmetric matrix. So whatever there is upwards, upper triangular, it would be similar in the lower triangle as well. So same thing if you see with C. So C has an edge with A, B, E, and D. So if you see for C, A, B, there is no self connection, D and E, right? And same thing if you see in this symmetric way, A, B, D, and E, right? So this is adjacency matrix, and this is basically, you can say, the base of graph neural networks, because the graphs are represented in the way of adjacency matrix. There is some more optimized way as well, but we'll not be looking into that. We'll be looking at the adjacency matrix only. So yeah, if edge is present, we'll have 1, and if edge is not present, we'll have 0. Now consider if we have a self connection there. For example, A is having a self connection, then at the diagonal value, there would be 1. So all these diagonal values where we have 0, will turn to 1 if all these have the self connection. So currently there is no self connection, we'll leave it as 0. So if the graph is weighted graph, means for example, if there is a weight here, 10, 3, 5, something like that, then instead of this value 1, we'll change it. So for example, A to B has a weight of 3. So instead of 1, it would turn to 3, as you can see in the second image. 3. Now consider C to D. C to D has weight 4. So for C and D layer, so here we'll be having 4. Same C and D layer, we'll having 4 value. So yeah, weighted graphs can also be represented as adjacency matrix as shown here, right? There is another type of matrix that is also required for graph neural network, that is the degree matrix. What this degree matrix suggests is a node is connected to how many other nodes uh, that can be decided based on the degree matrix. For example, here A is connected to B, C, and F. So basically 3 nodes. There is no self connection, so it will be 3 nodes. So, and it's a diagonal matrix. So it's symmetric diagonal matrix. So if A is, A is connected to E as well. So 4 nodes. So you can see A is connected to 4. And similarly, B is connected to just C and A. So there are 2 nodes. So these are basically the degree value of the graph. And these are again a square matrix and a diagonal square matrix, you can say. So rest all the values are 0. So this is the degree matrix of the graph. Now we'll go to the Laplacian matrix. So again, this is a very useful matrix. So it suggests how smoothly the graph is connected. And it is just the difference between the diagonal matrix and the adjacency matrix, nothing else. In simple mathematical term, it is just this L is equal to D minus A. So it suggests how smooth the graph is, or you can see it measures the smoothness of the graph. So as calculated in the previous example, these are the degree matrix where the diagonal elements are there. This is the adjacency matrix without weights, where all the diagonals are 0. So this has no self connection. And when you subtract it, you get something like this. So this is just the element wise subtraction, and we get a Laplacian matrix out of that. Right? So these are the 3 main important matrices